Welcome you all for the video lecture. In this lecture, we are going to see what is eigenvalue and what is Eigen vector as the continuation of linear algebra, which we seen in our previous lecture. So, what is eigenvalue and what is eigenvector? Why do we study this eigenvalue and vector in linear algebra? See, both eigenvectors and eigenvalue are used to reduce noise present in the data. Both terms are used in analysis of linear transformations. They also used to eliminate features that have strong correlation between them and also help them in reducing overfitting. These values revolve around the concept of matrices. Matrices are used in machine learning problems to represent large set of information. Eigenvalues and eigenvectors is about constructing one vector with one value to represent a large matrix. Eigenvectors has direction when it is plotted on xy chart. Since it is a vector, obviously it will be having direction. But the difference between normal vector and this eigenvector is the eigenvector will not change its direction when any linear transformation is applied. It changes only the scalar factor, not the direction. What is eigenvalue? The scalar factor applied on eigenvector is called as eigenvalue. Now let us see what is the use of this eigenvalue and eigenvector. And let us try to understand the use of eigenvalue and eigenvector with some example use cases. Assume that you are building a forecasting model which consists of large set of features. So hence it is difficult to understand and visualize the data. Then we maybe apply one hot encoding or some other encoding technique to understand them better. But this encoding technique would occupy more volume of space. To handle this, we will be applying component analysis. This is one of the key strategy which is used to reduce dimension space without losing valuable information. Principal component analysis, one of the most widely used component analysis technique to reduce the number of features present in the data without losing any useful information. Here, eigenvalues and eigen vectors uh, are the basic concepts behind this principal component analysis. Eigenvalues and eigenvectors have their importance in linear differential equation where we want to find a rate of change or when we want to maintain some relationship between these two variables. In example, they may be used in facial recognition techniques as eigenphases. They also can be used to rank items in a data set. Eigenvalues and eigenvectors provide summary of a large matrix. The eigenvector is an array with n entries where n is a number of rows or column of a square matrix. Please note that it should be a square matrix, means that number of column is equal to number of rows. The direction of an eigenvector does not change when the linear transformation is applied to it. This is where the eigenvector differs from the normal vector. Eigenvalue is which is represented using the alphabet lambda, which is represented as a into x minus lambda x is equal to 0. It means that when we multiply a scalar to the vector x such that it is equal to the linear transformation of matrix A once it is scaled by eigenvector, we can say that A minus lambda I is the determinant of a matrix. This A into, the determinant of matrix into x is equal to 0 if this x is a eigenvector. Here this diagram shows example of eigenvector. You just see the when we multiply eigenvector with eigenvalue lambda, the value it stretches the direction, but the direction does not change. Only the change in the magnitude. Here it stretches. If you look at this diagram, the first one corresponds to non-eigenvector because when linear transformation is applied, the direction is getting changed. So hence it is a non-eigenvector. Whereas in the second diagram, when we apply, when we multiply it with eigen vector, uh, the value, it stretches its direction, not changing the direction. Similarly, here in the third diagram, it compresses the value, whereas in the fourth one, it is in reverse magnitude, but the direction is not changed. So the last three diagrams corresponds to eigenvector, whereas the first one is example for non-vector. If any vector which changes its direction when linear transformation is applied, then it is non-eigen. Otherwise, it is a eigen, but it has to satisfy equation, this equation. Ax minus lambda x is equal to 0. That equation must be satisfied for any eigenvector.